This video introduces you to M.dot signal span calculation program. For a given site, depending on the configuration, we need to come up with the strain pole layout and the span layout with attachments, or what we call the signals, to control traffic. So there are multiple different guidelines. So this is one of the M.dot publications called M.dot signal head placement in box spans. So there can be different configuration, but this is a box span showing how you're supposed to have the signal heads placed and oriented. So there are different guidelines like that. So there are depending on the layout. So in this example, we are going to look at a specific configuration. So for a given site, we can have 4 spans if we go with the box span configuration, and also we can have some tie-offs. So in this one, we have the 0.2, 3, 4, and 1, and also 5 and 6. So 0.2, 4, 5 and 6 have poles, and then the 0.3 is connected through a tie-off to the pole. 0.1 is connected to pole at 0.5 through a tie-off. Then it has 4 spans. So there are different configurations. So there are, instructions are provided in this spreadsheet. So you can see there's another configuration called diagonal span. So this one has 1 span with 2 tie-off. Tie-off 1 at 0.1 connects to 0.4. 0.4 has a strain pole. And then tie-off 2 at 0.1. So this point has 2 tie-off. This is tie-off 2 at 0.1 connects 0.1 to 0.3. 0.3 has a strain pole. Similarly, 0.2 has 2 tie-offs. Tie-off 1 at 0.2 connects 0.2 to 0.5, where 0.5 you have a strain pole. And then this one, 0.2 connects to 0.6 through another tie-off, is tie-off 2 at 0.2, and 0.6 has a strain pole. So this is like what we are looking at as a box span or suspended box span configuration. In this one, 0.4 is connected to 0.6 through a tie-off, 0.2 is connected to 0.5 through a tie-off. So these are typical configurations. So we need to come up with a design that's going to be within the limits defined by the standard details. For that purpose, this particular spreadsheet is developed, tool is developed. It has instructions, it has given you the limitations, like the horizontal force can be more than 1500, and also it provides different color codes with cells. Yellow cells requires your input. The others are some reference or calculated values, and some key values we call. Key values are the ones that we are going to use for the checks. If the checks fail, then it will be highlighted in red. So when you have a satisfactory design, you should not have any cells with red color. So the spreadsheet starts with span configuration. So you will have preamble page, changelog page, instructions page, and span configuration. In addition to that, there will be some light or bright yellowish color highlighted sheets with some equipment weight, work authorization, and some other information. There should not be any light bluish color pages. They are generated actually later, even though they are included in this example, because we have already developed part of the example. So this example, the typical design start with input data into these yellow cells. So in this particular case, because we already have identified a configuration for the site, it has 6 points. As you could see, there were 6 points. Okay, 1, 2, 3, 4, 5, and 6. There are 6 points, and then 4 spans. And then we have 2 tie-offs and 4 steel poles, strand poles. And then we can mark the quadrant based on the junction, the orientation of the intersection. And then for each location, we need to provide northing and easting. For poles, we need to provide the elevation at the top of the foundation of those poles. So you can't arbitrarily design this or come up with this. This needs to be provided, or it can be developed through a conversation with multiple stakeholders. And we have a separate video explaining that process. So you need to have access to this information. So once you have that information, you can basically input that information over here. It will calculate some x and y coordinates and also average northing and eastings. If needed, you can offset x and y coordinates so that it will automatically update these numbers. So once this information is provided, the next step is to provide span configuration. So in this particular one, we have 4 spans, 1, 2, 3, 4 spans and 2 tie-offs. So we provide that 4 spans and 2 tie-offs. And then each span we have point A and B. So basically span 1 connects between point 1 and 2. So we provide that as point A and B. So point 1 and 2 connects span 1. If we look at span 2, it connects point 2 and 3. So you see that here, 2 and 3. So likewise, we define the connecting points for spans and also for tie-offs. So tie-off 1 connects point 1 and 5. So tie-off 1 connects point 1 and 5. And also when you have tie-offs, we need to provide main spans that are connected by the tie-offs. So main span A and B for tie-off 1 is going to be 1 and 4 because tie-off 1 connects span 1 and 4. So we need to provide 1 and 4. Tie-off 3 connects span 2 and 3. So span 2 and 3 are connected by tie-off 3. So we provide that information. In addition to that, we have to provide the elevations at the grade center lines to calculate the clearance. So that information also you need to have access to. So once you have that information, you populate this. So it will automatically calculate span lengths and pole base elevation, pole, and also x and y coordinates of each point. So once this information is completed, next you have to go and generate span calculation tables. For that, you click this button and it should open up light blue 6 pages for this example. So 6 sheets, basically 6 sheets will be added to this spreadsheet. So they will be labeled as 1, 2, 3, 4 to represent the spans 1, 2, 3, 4 spans, and then 2 other pages to represent tie-off 1 and tie-off 3. So those will be light blue color tabs showing the sheets. Now when we go into sheet 1, so sheet 1 also requires some input data like horizontal force, whether the signal heads are tethered at the bottom or top, or they are not untethered. So you have to select that. Okay, so based on that, the values will change in this one. Okay, so then also you can define what is the design standard. So whether it is 20-21 or one of those, or 22. Based on that, the numbers will change, the conditions will change. So we select what is the design standard. And after that, we have to check if all the conditions are satisfied. But before that, we have to look at the span length. So span length is 121. So that is graphically represented over here. We have the pole location and the other pole location. So along the cable, the wire, we have the length as 121. Then depending on the layout at the site, we need to identify the type of signal heads and their locations. Then this span is divided into 1 foot increments. So along the span, we have to go and select the heads to be attached. So depending on the configuration, you select one, and at corresponding locations you select signal heads. So once we do that, so all the numbers will be populated and the conditions will be checked. As I mentioned previously, there are like sag limits. So this one has sag 6.91, that's greater than 6.5, so the condition is satisfied. But for some reason, if someone started this with like 1000 pounds horizontal force, that will stretch this wire much higher than what we had previously. So that will reduce the sag to 5.47. The condition is not satisfied because these ones have tie-offs, so it should be 6.5. In order to have a higher sag, we need to reduce the tension. So we can go, let's say 800. It's still not satisfied because it's 6.31%. So that's why like 700, 750 you can try. So as long as it's greater than 6.5, the conditions are satisfied. In addition to that, in this sheet, you need to also go and check point A, that means point 1, point B, that means point 2, connecting this span. And also you need to define how high the wires are connected, or the cables are connected for the span at each pole. So these are 30 feet from the top of the foundation. So once you define that, there will be additional conditions checked. If everything is correct, then you can assume that satisfies all the conditions and they are within the limits defined by the standard designs. There are standard design sheets provided by MDOT. So then we say, okay, all the conditions are satisfied. If you're looking at standard details, so MDOT has multiple sheets. They call SIG 20 or SIG 21. They call the traffic signal strength for loading table and design criteria. These sheets describe the specifications used, assumptions, design process, and some of the values used for the design, as well as the limits. As I mentioned, there are some wire sag limits with and without tie-offs. So with tie-offs is 6.5, without is 5. So that's the sag. So likewise, there are different limits and loads defined. For example, the span wire loading table tells you the maximum load that you can apply for different span lengths, as well as the area perpendicular to the wind of the attachments, like signal heads, depending on the wires are tethered or the signals are tethered or untethered. These are the maximum values used for the design. So basically the upper bounds. So when you calculate the value, so when you come up with the configuration and check that through the spreadsheet tool, it will automatically check this with these limits. If these are violated, then it will give you the red cells telling that your design is not within the envelope provided by the standard design. So you need to revise your design. But in this particular case, everything is satisfied for span 1. So you can select number 2, that bluish sheet. So that will make it to span 2. And then you go through the same process, okay, and check all the limits after defining the heads, types, and their locations within the span length. So in this particular case, span length 143 feet. So you define, and also in this diagram, you see the cable, you see the attachments or the heads, pole, as well as the minimum vertical clearance required, like 17 feet. That's also marked over here. If that is violated, so some of these will become red. Again, similar to the previous one, you go point A and B are checked. You define the heights from the bottom of the top of the foundation to the connecting point on the poles. Then you repeat this process through page span 3, okay, and for the span 4. Okay, so like certain cases, okay, the conditions will not be satisfied, so you need to look at how to address the conditions to have these conditions satisfied. Similarly, at the end, like when you go into tie-offs, so there are again, we had to say tie-offs, whether their heads are top tethered or bottom tethered, depending on how you selected them, what signals standard you're using. So after all, these three numbers should become 0 and then everything should be okay. Now, as you see, this shows not good because these numbers are there. They're not in equilibrium. So we need to change the design to get all these conditions satisfied. Otherwise, your design violates the standard details developed and presented in these signal standards. Okay, so 20, 21, and 22 details. So they are not acceptable for that particular site. So you need to figure out how to change this. So we'll need to look at examples and learn the process, but this is the overview of the spreadsheet and how you can use the spreadsheet tool from start with span configuration going into specific sheets for depending on the span to input the data and check the conditions.